All right, so what we're going to be talking about today, or right in this video, is let me pull it up. Here we go. Our running water, or basically rivers. Okay, so you guys are familiar with the rivers. Everybody knows what a river is, but let's talk about some of the details surrounding rivers in a little bit more specific and scientifically here. So Um, some of the objectives, I want you to be able to list the major reservoirs. I've talked about this before. We'll see that in the first slide here coming up. Sometimes we'll refer to those as sinks. Where do we find water on the planet? Describe different drainage basins, discuss stream flow, right? How does it move? Um, Summarize the ways in which we're going to have erosion and sedimentation build up, contrast bedrock, alluvial stream channels, different types of river channels. I'll also talk just briefly about dams as well. All right, so something you guys are familiar with, I've shown it a couple of times. It's actually on a couple of the worksheets, and that is understanding where the water is on the planet. Most of that water is marine. We already talked about oceans a bit. 96.5 percent of the water is in the oceans. Only 2.5 is freshwater, and then finally we get over here to rivers. Over here with the rivers, we only have 0.03% of all the water on the planet. So we're going to have a whole lecture on rivers, and they're important for our planet and for society, etc. But just recognize that it's only a small fraction of the water on the overall planet. So again, fresh water, 2.5%. That's not a whole lot of the water on the planet. Most of that's locked up in the glaciers, 69% of all the fresh water. And then the groundwater is our next component. Again, we're talking about breaking down the fresh water. So now we're going to just look at the fresh water, ignoring all this 96%, and just looking at this. So 69% of the fresh water is glacier, 30% of fresh water is groundwater, so underneath our feet. It's kind of cool. And bring up the next bullet point. Only about 0.03% is all the others. And now that's also going to include the atmosphere, lakes, things like that. So even smaller amount, if you think about it, represented as our rivers. So if we look at how we break that down, so you know, most of that outside of the ice sheets, most of that's going to be groundwater. Okay, so very small amount represented in our lakes and rivers, etc. Okay, all right. So what is that hydrologic cycle, or sometimes we just refer to it as the water cycle? Um, we have various states of movement between the water. So as you know, I don't have to probably say this too much, but water can have three different states. We can have a liquid water, right? We can have a vapor or a gaseous state. Okay, that will be like humidity in the atmosphere. And then, of course, we can have solid water as ice. And it's going to move from one state to another through various mechanisms. So we have precipitation, of course, rain, right? We have evaporation, where it's going to evaporate um, off the surface of a water source, or maybe just off of the ground if it's been raining, etc. We have infiltration. That's where the water will then run into the ground, and then it will become groundwater. We have runoff, where it doesn't get soaked up into the ground, but does run off. Usually, this will then lead to rivers and streams, of course. And then we have something called evapotranspiration. I mentioned this before, but it's quite important, and it does influence the weather or the humidity of particular regions. And that's a mix between what's called evaporation and transpiration. So evapotranspiration is includes the water vapor that's being released from plant material, plant life, right, trees and such. All right, let's take a look at a video. I like my videos, so we'll go ahead and we'll watch this video on water cycle. Okay.
water on Earth today, every drop, is all the water there has ever been on the planet. Fresh water is actually millions of years old, the same water flowing in a continuous loop, falling as rain and snow from clouds to the Earth's surface, running in rivers, pooling in ponds, flowing from faucets, irrigating crops, traveling through plants, generating power, eventually evaporating into the air and condensing into clouds again.
Why is there life on Earth? And the reason there's life on Earth is because Earth has this perfect water cycle.
The water cycle, so simple even small children understand the basics, yet so complex the most advanced Earth scientists, hydrologists, geologists, and biogeochemists are studying every part and process.
The water cycle is fascinating. It's something that's around us all the time, and yet we don't really understand it.
How to summarize what is known about the water cycle? With two words: flows and stores. The water cycle is a series of flows of water between various water stores or storages. Clouds in the atmosphere.
There's always a little bit of water in the atmosphere. We talk about relative humidity. It's a humid day, it's a dry day. Either way, there's water, sometimes a little, sometimes a lot.
There's a lot of water in the ocean, 70% of all the water on Earth. In the ice sheets and glaciers, 2/3 of all the fresh water on Earth. In the snowpacks atop mountains like the Sierra Nevada. In the Great Lakes, in rivers and streams, in reservoirs and watersheds, in wetlands, in the soil, in and on plants and trees rooted in the soil, and beneath the soil, in water tables and underground aquifers like the Ogallala High Plains, which runs underneath parts of 8 states from South Dakota to Texas. All this storage is temporary. Water in all its forms is always in flux and always moving. And there is a name for every kind of movement in the water cycle, starting with precipitation.
Precipitation is the process of water falling onto the surface of the Earth. You can have precipitation in many forms: rain, snow, hail.
Rain is falling water in liquid form. Snow, ice, hail, and sleet are falling water in solid or frozen form. Fog and mist, falling water in gas or vapor form. Precipitation that falls directly onto the oceans becomes part of surface ocean and can be churned by wave and wind action into ocean currents. Rain and snow that falls directly on rivers and streams becomes one part of stream flow. Rain that falls onto land takes a different path to the river, as does the snow and ice that falls and collects on mountaintops when temperatures warm.
When snow melts, some of it runs through the snowpack and goes into small streams, tributaries that feed into large rivers.
What about that precipitation that falls on and over land? Some is intercepted by vegetation, plants, and trees.
Like you might imagine someone in the game of football intercepting a pass, either raindrops trying to come to the ground and the leaves on the tree intercept them before they hit the ground.
And the precipitation that does hit the ground, it can run off if the ground is hardscape, covered with asphalt or concrete, or if the soil is too wet or saturated to absorb more water, like an over-soaked sponge. Otherwise, precipitation infiltrates the soil surface, percolates into the ground.
Think of it as the water percolating through your coffee grounds in the morning. Gravity continues to pull it downwards so it will move
through the topsoil, into spaces between soil and rock particles, down to bedrock and further into fractures, into deep underground aquifers. Even groundwater here is moving sideways or laterally, discharging toward a river, lake, or the sea. Generally, the deeper the flow, the slower the flow.
Some of that fractured water might take a very long time, thousands to millions of years to get out.
And how does water get back out into the atmosphere? It evaporates, is turned from a liquid into a gas or vapor by the heat of the sun.
If you put a bit of water into a bowl and you set it outside on a sunny day, it's going to disappear. It's still water, it's just in the form of a gas rather than the form of liquid.
Water evaporates from every wet surface, even from wet air. Some rain and snow evaporates into the air while falling. Water evaporates through our respiration and perspiration, and from plants through transpiration. Trans means through or across. Plant roots draw up groundwater.
And plants pull that water up through their stems into their leaves and then release it back out through evapotranspiration.
Evapotranspiration, a spelling bee worthy term for evaporation from soil and water surfaces, plus transpiration from plants. Evaporated water molecules are tiny enough to flow into the air, mix with smoke and dirt particles in the atmosphere, cool, condense into visible masses of water vapor, clouds. Winds move clouds into colder air, water droplets collide and merge, grow bigger and heavier until they are so heavy they fall again as rain or snow, sleet or hail. Precipitation, collection, runoff, interception, infiltration, percolation, discharge, transpiration, evaporation, condensation. The water cycle.
Very cool. So hopefully that gives us a real good sense of how water is moving throughout our planet. Now, today we're going to be talking primarily about rivers, but I like to make sure we have a great foundation in the hydrosphere, understanding the different reservoirs, right? Or sources or sinks, right? Goes by many terms. Oh, before I get too far along, the one thing she had mentioned, this is why you have to take everything you see online with a grain of salt. So if you notice, she said oceans represent 70% of the water on the planet. What she meant there is it covers about 70% of the surface. I think that's what she meant, because she made a mistake there. So the oceans contain about 96.5% of all the water on the planet. And they cover about 70% of the surface. So just as you're looking online and you find different information, you got to be aware that sometimes it can be inaccurate. So be careful out there. All right. So moving on, let's talk a little bit more about rivers. When we talk about rivers and we talk about the amount of water, right? It's going to be related to a lot of factors. We have, of course, precipitation, or the amount of rainfall. It could be snow as well. But we're talking about the intensity and the duration. That will then relate directly to the amount of runoff. We actually have a seasonal creek here on campus, real close. And there are particular points in time, usually around August, where it's totally dried up. And then there are other times where it's really raging, tons of water. Again, the intensity and amount and duration of that rainfall is going to relate to the rivers and streams, right? And the amount of water flowing through them. This will also relate directly to the amount of water that's already around. So again, if you're in a really rainy environment, that'll relate to the amount of runoff versus getting captured by the land around you. It's going to also relate to the nature of the surface material. Like she said in the video, if it's hard surface like asphalt, of course, it's not getting soaked up. So it's all going to run off, right? But if it's different material where it might be a little bit more loose material, sandy material, it's going to really soak up that water a little bit more. You won't have quite as much runoff. The slope of the land. So is it going to pool and collect in certain regions, or will it run off and down and make its way toward the oceans? And then, of course, the extent and type of vegetation. So if you don't have vegetation, you're going to have a lot more runoff. More vegetation will capture a lot more of that water as it's running, as it's kind of making its way down a particular slope. When we think about rivers and streams, we're thinking about their drainage or movement from a higher elevation to a lower elevation. When we do that, we consider something called a drainage basin. Drainage basins are separated by what are called divides. And divides, think of those as like ridges, but they can be even more substantial than that. But here's what we have is a divide where on either side, the water will go one direction or another, depending on where that raindrop falls, okay? And as it does that, it's all gonna eventually collect. So we have these tiny streams here in this drainage basin, and they're all collecting into one major stream or river. And as they do, they're gonna all kind of collect. And finally, they make their way as one united drainage of that entire drainage basin. Does that make sense? So just something, I know it's obvious, something you're probably familiar with, something to think about though. Here's a neat one to think about. It's kind of cool. So Columbia River, right? Columbia River here, Missouri River here, Mississippi, etc. What's kind of cool about this is if you think about these rivers, one is going to the Pacific Ocean over here, Columbia River. Okay, it's just to our south. So we're here in Lacey, and to the south, so separating Oregon and Washington, for instance, actually goes up into Canada. There's another river that moves from over here toward the Rockies over here and connects into the Columbia, which then exits into the Pacific. That river, I'll show you in a second, it's called the Snake River. It's a really cool river. But the important thing to understand is we have one river system, right? One drainage going here to the Pacific Ocean, another drainage system, right? Drainage basin, right? Heading over this direction, it's going to end in the Gulf of Mexico, or basically the Atlantic is a better way to think of it. And that's going to include the Missouri River and Mississippi rivers, huge rivers, by the way. All right, but why am I showing you this? Just to emphasize this idea of drainage basins and divides. So if you think about it, what do you think is going right through here? Okay, this is where the Rocky Mountains are. Okay, so the Rocky Mountains are going to represent the divide, and then these will be the relative drainage basins. So you have one emptying here in the Pacific, one emptying here, ultimately, mixing with the Atlantic. Okay, you can ignore the Yukon for now. Okay, this is just showing the amounts of water in each of these, but that's not the point I'm trying to make right here. But you can take that into account and see these various sizes of these rivers. Some of them get quite large, like the Mississippi. All right, but back to this point. So over here is the Columbia, and you can see just based on this image, it's kind of cool how they make the lines bigger or thicker, depending on the amount of water that's discharging from that drainage system. All right, so here, right here in this point is the Snake River, and it's going from here all the way around, right? Then it connects into the Columbia, so this Columbia connects into the Columbia, and then ultimately exits into the Pacific. On the whole other side of the continent, you have the Gulf of Mexico or the Atlantic. You have the Mississippi River, which is coming from the Missouri River, which is coming from way over here. Okay. Now, what's kind of cool, and in here we also have something called the Yellowstone River. What's kind of cool is right along this point, right, is the Continental Divide. So that divide is really going to help create these two drainage basins. What's kind of cool is if you've ever been to Yellowstone National Park, what's really cool about it is you can see in relatively short amount of time, maybe a half-hour drive, you can go from one river, the Yellowstone River, drive a little bit south, and you can go to the Snake River. Okay. Now, why is that cool? Well, it's cool because you're talking about 100-mile difference, less than that, maybe, a really short distance. And here you have one, if you go swim in either of these little rivers, you can go and you can swim in water that after leaving you is going to make its way all the way over here to the Atlantic Ocean. And then you drive a little bit south, right? And you see another river system that's going to make its way all the way to the Pacific. It's really kind of cool. And it's neat to think about that you're basically standing on a divide, right, of the continent, right? And if you're able to imagine like water kind of rolling downhill, on one side it's going to roll all the way down here to the Pacific. On the other side, it's going to roll all the way down to the Gulf of Mexico. Really really kind of fascinating to think about in that regard. Okay, and you can see that divide here. You see it here. You know, I'm not drawing the line exactly right, but you can see that continental divide kind of moving its way all the way up here, right? Anyway, kind of cool to think about stuff like that, right? All right. Drainage basins, so back to that. Drainage basins are divided into three parts. We have sediment production, transport, and then deposition. Production typically is going to happen the most up in the headwaters. We're going to have water kind of, we call it turbulent flow, but that flow is really going to be just kind of rough, and it's going to really aggravate the geology underneath the water system. It's going to break it apart, and it's going to then erode that material. Then we have transport. It's going to transport it, especially the lighter stuff. It's going to transport it as far as it can. And then it gets to what we call the zone of deposition. Sometimes we call this the delta or the mouth of the river. All right. And that's where a lot of that sediment is going to be ending up dropping out and deposited into the system around it. All right. We have four main drainage patterns. The first one here is called dendritic. This is probably what you're most familiar with. This is most river systems around us here in the Pacific Northwest. And then we'll have something, and you can have meandering and added features to this on top of this, but dendritic, so think of it like, looks like a nerve or a neuron in our body or something. It's kind of cool. And so what you can imagine here is this is the drainage system, and then these might be within a valley or a canyon, and these are kind of coming down off of the ridges around that particular system. So you can see it here. And then we also have radial patterns. So when we go up to Mount Rainier, you're going to notice that these rivers are all kind of stemming from that, from the glaciers on that mountain, or runoff from that mountain. And as they do, they form this sort of radial pattern. So in the middle here is, you can say, Mount Rainier, for instance. And then off of that, you're going to have these different rivers, like this might be Nisqually River, for instance. Okay, so kind of cool. So that ends up giving us what we call a radial pattern off of that. And if you notice, off the radial pattern, we also have the dendritic kind of laid on top of that as well, right? So this is dendritic, but the whole system here is radial. And we have some others that we don't really see here. You'll see some of these, in the Midwest, Kansas, etc. Rectangular patterns, right, where they're kind of flowing. It's usually flatter ground. And then we can have what's called a trellis pattern. You see this in more desert environments, rocky desert environments. So you see this in Utah, you see this in New Mexico, Arizona, things like that. So it's kind of a cool way that these rivers run. They're still trying to find their way out, right? But because of larger rock, right, getting in the way, they're going to have to kind of travel and make their way in unique ways. And oftentimes that forms like this kind of trellis pattern as they finally make their way through and on their way out. Okay, kind of cool. So anyway, just something to think about, these different types of drainage systems that we see on the planet. Right, stream flow, it's going to be related to the gradient or slope. In this case, we might have a very steep slope, we might have a very shallow slope. It depends on the particular terrain around it. Again, everything's related, right? Geosphere and hydrosphere, really talking about two different points coming together to influence stream flow here. So we have a couple of different things to think about. So what is the shape? Is it V-shaped or is it more of a U shape, right? And what does that mean? I mean the stream bottom, right? Is it slicing its way through a canyon, or is it more laid out, like more of a flattened region? And so the river system, if you were to take a slice through it, does it have a shape to it? What does that shape look like? Is it V and very narrow toward the bottom, or is it more of a U-shaped? And these different shapes or channels can then relate to the actual velocity of that. Okay? Typically, V-shaped is a little faster than if it's U-shaped and a little more spread out, right? The size of the channel. So is it really wide channel? The wider it is, the slower it will go. The more narrow it is, the faster it will go. And then how rough is it? So if it's rough, right, rough terrain, meaning boulders and rocks, trees and logs and things like that. If it's really rough, what that will do is it'll actually slow down the river or the water system itself. So the roughness of that particular terrain that the water is trying to flow through will also slow down or influence the speed of the water there. There's stream flow, right? All right, and then discharge, how much water is flowing through it. We won't get into too much detail, but basically more water equals faster stream flow. So there's a pretty close relationship between the two. So if you're able to take and look at the river based on elevation and get a profile, and I like this one here in the left because it kind of mimics what we see with Nisqually River. So Nisqually River begins way up high, 7,000, 8,000, well, even maybe a little higher than that, feet up on Mount Rainier, and it's going pretty steep as it's making its way down. And then, of course, as it gets closer to where we are now with Lacey, et cetera, that water goes much slower, right? Or not slower, but goes much flatter, right? And so you can look at profiles of these rivers, and most of them have this fairly typical shape. Not all of them, but many of them. Some, the headwaters may start here and they're just not going very far, period, right? Okay, so depends on the system, but this is fairly typical, especially here in the Northwest, which we'll try and keep it with a Northwest flavor here, a Washington-centric earth science course. All right, longitudinal profiles. This is a crazy graph. I'm not going to go into all the detail, but I do want to point out one thing, and that's regarding flow. So if you look at the flow, all right, the headwaters relatively slow, but as we increase in the amount of water, that's what we call discharge. We increase the amount of water. There's a pretty close relationship between discharge, or the amount of water, and the flow velocity. So how fast is it going? Okay, so as it's making its way toward the mouth, that flow velocity increases and increases, and it finally kind of gets to a maximum and it kind of slows up. And that depends on the terrain, of course, but as it's making its way down, that water gets a little bit more fast as it's moving along, and that's related to the amount of water, right? Okay, and again, I'm not going to get too much detail into this particular slide, but understand, you can look more into this graph to get a little bit more detail if you want. All right, some other characteristics of rivers, just to get us thinking about rivers and some of their characteristics. We have a couple of different flow patterns, and they can be, you can see them, pretty much all at one point, or maybe you'll have, pretty standard differences between river systems or states of the river itself. We have laminar flow. This is really kind of calm water, moving really slow, not slow, but calmly. Okay, that's just the best way to put it. And we can see it right here. This water is not pooled. It's actually moving, but it's moving in what's called laminar flow. If you go just before that, right up in this region here where the rocks are, this is what we call turbulent flow. Okay, so next time you're standing near a river and you see this, rough water kind of moving and churning and all that, understand that the velocity is the same here, even though it doesn't look like it. It's just different types of flow. So here is turbulent flow, and down here is laminar flow. But what this is saying right here, this water is not standing still, right? It's still moving along, even though it doesn't look like it. So take a closer look next time you're looking at a stream, and don't just take everything for granted. And of course, this is, crazy. This is Grand Canyon, turbulent flow. That's an extreme example. So you can get a sense for the differences in the ways the rivers can flow, generally speaking. All right, so then we'll talk about erosion. So erosion is the breakdown of solid material. It's going to go through a couple of different aspects here. We're going to have what's called transportation. That goes through a couple of different ways. We have dissolved load, right? That's the stuff that's basically dissolved in the water, and you can't really see it. These would be the minerals and things like that, the salts, right? As I talked about before with the oceans. These dissolved load components, usually minerals, these are going to make their way to the ocean, and that's what will in part lead to the saltiness of the oceans. We also have suspended load. This will be evident when we go to Nisqually River. You'll see that it has a color to it. It looks kind of milky, right? And that milkiness is due to the suspended load in that water system. And then we have bed load, and bed load can be anything from very, almost microscopic, small bits of rock to larger rocks, depending on the flow of the river. So the higher velocity, the larger the bed load can move, right? The larger pieces of the actual solid material that will be moving along. And there are different ways that they'll move, and we'll watch a very short video, not video, but a little thing showing this, okay?
Stream sediment movement. Rock transported by the flowing water of a stream is known as the stream load. The stream load moves in several different ways. Some compounds, such as salts, may be dissolved in the flowing water. Very fine particles of clay and silt are carried in suspension without touching the stream bed. Larger particles, such as sand, may jump or bounce along the bottom in a process called saltation. The largest particles, such as gravel and cobbles, slide or roll along the bottom in a process known as traction. Material moving in solution is known as the dissolved load of the stream, while sediment moving in suspension constitutes the suspended load. The larger material moving by saltation or traction makes up the bed load of a stream.
Pretty cool. Just, some of the stuff, just hopefully getting you guys thinking about, your earth in different ways, appreciating stuff that you normally might not even think about. So again, next time you're standing next to a river, think about some of these things we're covering. It's kind of interesting stuff. All right, so dams, not going to get too much into them, but I do want to point them out because on our journey, investigating Nisqually River, we're going to be, I'll pull it up. We're going to be discussing dams because there is a dam on the Nisqually River. It's called the Alder Lake Dam. Here's a picture of it, okay? And it actually creates Alder Lake, right? And so I want us thinking about the river, right? From the mouth of the river, that's where we're going to start actually. And then we'll go up to Mount Rainier and we'll pass by Alder Lake, which is up here behind the dam. And we'll think about what are some of the impacts and implications of a dam. So if we think about a dam, things I want you to consider outside of like impacts on fish and how do fish get around a dam? What does that do to their livelihood, right? It's quite impactful on the fishes in that system, etc. So the fish, really can be hindered by this, as well as other organisms too. But I want you thinking also about, because it kind of attaches itself to the previous topic last slide, and that is soil or sediment movement. So how do we not prevent all that soil and sediment from getting stuck or trapped behind the dam, right? Think about what's happening here. So you have all this material coming down the river and making its way out to here, okay? As soon as we put a dam in there, one of the things that's going to happen is we'll have lack of that movement of soil and sediment. What ends up happening is we'll have, behind the dam, we'll have all this buildup of sediment in this area here, as opposed to out here. So that sediment, the nutrients that are flowing through there, a lot of that's getting stuck and trapped in that particular lake up here. So it's just something, I know we always think about fish, right? Fisheries, etc. oh, it's going to impact the salmon. Yes, it does, but I want us thinking then maybe a different light and think and consider the sedimentation. So anyway, it's kind of interesting to think about from that standpoint. And so that will affect a lot of the geology under this, the nutrients, right? And it may even impact the what's called the delta or the mouth here, where we don't have as much sediment depositing here. So that will affect a lot of the characteristics of this stream or river downstream of the dam, right? So things to think about. And again, when we go take a look at Nisqually River and go up to Mount Rainier, we'll drive right by Alder Lake. So we'll talk more about Alder Lake in the future. All right, this is just kind of fun. Hopefully it's still up. This one I didn't pull it up. I didn't get it ready ahead of time. So let me pull this up.
If you're a
boy.
Washington homeowner, 2022 is your last chance
Sorry.
to go solar. In December of 2020,
So there's Elwha River, northern Washington State, up just north of the Olympic National Park, right? So to give you a sense of where we are, Elwha River had a dam on it, and they were removing the dam. It's kind of cool just to think about this. Kind of neat video too. Here we go. Okay.
Chinook 6055.
Coho 115, 108.
It depends on the species, but we have a broad range, and they're all kids from infants to basically teenagers. Seeing the evolution is what it's ended up being. In particular, in the nearshore, it's been a dramatic transformation. The nearshore is a very important bridge.
So that gives you a sense for where we are. So there's Olympic National Park. We're down, way down here near the W. Okay. And we're talking about a dam right up in this area. One thing that's interesting is, and I want to pause for a second just to point this out. I don't think they do a great job explaining all the nutrients and all that, but it is there. So think about the sediments and the nutrients, the dissolved load, all that able to really be transported much better now that the dam is removed. Has really a dramatic impact on the estuary, right? Which is the mixing of the fresh water and the salt water. It's kind of cool. Anyway, let's go ahead and listen to her.
Between the upland and marine systems, and it is a critical link between the two that kind of make both work. If you think about the Elwha watershed and marine systems as being a house, the nearshore component of it would be the nursery. And so it provides this wonderful little oasis of habitat and food and refuge. It's a very quiet place in a very tumultuous world. I've been working in the nearshore. I think I started my first conversations about the Elwha nearshore were in 1995. So just about 21 years. We're going to do 4 total. For our second one, we're actually going to walk up and around the corner and do a second set just around the corner here. We'll see Chinook salmon, coho, steelhead, chum, bull trout, and all of those are federally listed as being endangered species.
Go back 40. They are below the net.
The Elwha dam removals isn't just about pulling dams for fish passage, although that's certainly a big part of it. It's also about liberating wood and liberating sediment. And in the near shore, those two elements are what make our beaches. They're what make our kelp beds. They're what make our eelgrass beds. And those habitats are the things that are so critical for the function of the near shore. 100 years of sediment that's been trapped up in the watershed, it's roughly the same as 8 stadium fulls of sediment. Now that the dams are out, the visual aspect of it is so dramatic that the near shore has actually become the poster child for
I'm pausing here. Think about that. I mean, you know, she's talking about the nutrients and the sediment and all that. I mean, think about this. I'll just try to flick back and forth. So we have that particular picture, right? Fast. Oh wow. I mean, just dramatic difference in the mouth of this. So look at this whole area here. Watch as we go forward. Wow. Just 4 years later. I mean, there's just so much sediment, so much, you know, it was such a dramatic change after removing that dam. So much more than just enabling fish to pass through. I mean, that's really what I'm trying to get you to think about here is, you know, all the other details that we may be not considering regarding the nutrients and the organic material and the sediment and all that.
our dam removal project.
Really kind of cool.
This is the largest dam removal in the nation and certainly the first of its kind. And so nobody knew what was going to happen. But the good part is that the ecosystem is going to be restored from this action.
Pretty cool. Okay, so just want you guys thinking about dams and thinking about the whole system maybe in a slightly different light. All right, let's continue on. We're almost done here. And then we'll watch another video, which I think is just kind of fascinating to think about. The dynamic aspect of rivers. We'll come to that in a sec. All right, so there are different stream types. We won't get too much detail into this, but we have bedrock channels. Typically, bedrock channels end up resulting in like a steep canyon-like structure. And then we have alluvial channels, and these are more what we'll see in looser material. Oftentimes, these might be flatter as far as the way they've cut through the terrain. So here we can see Yellowstone River, and we can see these dramatic canyons as it's cutting through this hard bedrock, making its way through. And if you compare this to, say, the Mississippi River as it's cutting through loose soil, it's normally a little bit more wide open, not quite the V shape that you see with the bedrock channels. Generally speaking, we have a couple of different stream. You know, we're getting just a little pieces of all this information, but we have braided streams. We're going to see this. You can see this with Nisqually as we go up to Mount Rainier. You'll see braided stream systems, and then we also have. Oops, there we go. We also have meandering streams. So to some degree, Nisqually fits this bill. Not great, but does a little bit. As it makes its way down and it gets closer to the Nisqually estuary. But here we have something called Oxbow Lake Formation. So as these make bends, they'll make bends and then eventually just cut off or ignore the bend altogether. What that ends up forming, this one's not totally formed, it looks like, but what will end up forming is what's called an Oxbow Lake. Right, so this will eventually get cut off here as the river just continues to bypass it and make its way this way, and so it'll totally change over time. So this river system might form an Oxbow Lake here, right? But look, there's a big bend here, so maybe this will eventually keep cutting and form another Oxbow Lake. We're going to watch a video, a TED Talk video that shows this dynamic activity. Pretty remarkably. It's kind of cool. All right, so you know, getting into this a little bit more, going with a little bit more detail. Again, think about it. If you go to a river next time, think about all the details inherent within that river system. So here's something that's kind of cool. Is something to think about is the velocity. So if you look at the river and you're able to get a slice of it and take a look at the velocity, you see that as the river's bending, right, just a slight bend maybe over here, what we can see is that the velocity of the river is very fast on this side and pretty slow on this side. Okay, now what does that mean? What that means is we're going to have more cutting, right, erosion on this side as that velocity is really churning along and kind of digging into the bank of the river over here. Meanwhile, over here it's really slow. So what ends up happening is anything it's trying to pull along and carry, you know, as far as what it's eroded, it's not fast enough to carry it. And so it'll get dropped here. And what ends up happening is we have two things that form. We have what are called cut banks, and that would be this side where it's just cutting along and sort of digging into this. And then on the other side, we have point bars, and you see that over here, point bars, right? We can see this, there's one place, if you go to the Deschutes River, you can see this quite dramatically in certain points where you can see cut banks where it's just really digging in. And then directly on the other side of it, you'll see what are called bars or sandbars or gravel bars, where they're going to deposit a lot of that material. So here's another way to look at it. So here would be a point bar. You can see the gravel here getting deposited. And this would be where it's cutting in on this side. And so it's going to do that. Here we're cutting. The velocity is much faster over here, much slower over here. And it's depositing a lot of that gravel and silt and debris. You can just see it. Every time we see a bend, we're going to see that same type of feature. So here we are digging in. Oh, I wouldn't want to be living there, right? Okay. And then over here, it's going to be depositing, which is kind of cool. Okay. So again, really think about the river and what's happening, right? As it's making its way through. Okay. And I'm not going to show this video again, but this is a video showing this, this bend here. And it's kind of a cool video. If you forgot the video, it's basically showing that the terrain is lifting up, but as it's lifting up, this river, which formed this big, bend, this river is actually continuing to cut down and down and down and down, which is kind of cool. So the rock formations are coming up and the river is cutting, and they're both kind of having the same timing, right? Where the river is cutting as fast as the rock is actually lifting up. So here we see this in Grand Canyon, but we see it in the Yakima River, see it in portions of the Columbia River. Many rivers are showing this type of feature. Kind of cool. So again, it's caused in this case by uplift of the land while the river continues to cut its path. All right, so now we'll end with this video. It's a little bit long, but I think it's really cool to think about the dynamic nature of rivers over time, right? And we're looking at everything from right now, today, right? This minute, this hour. But think about rivers over time, which is kind of cool. All right, and we'll end with this video here. This is a TED Talk. If you don't know about TED Talks, you should. They're really cool. Okay, so you can go to YouTube or TED. Either way, most of them are posted on YouTube, and you can actually find lots of different interesting talks that are out there. Cool. Sorry, a little loud.
All right. Yes.
So this one's 11 minutes. We'll end with this. So bear with me. It's a little bit long, but it's interesting. I may not watch the entire thing. I may just go ahead and pause it, and you can get the PowerPoint and link to it as well.
Get up our picture of the Earth. The Earth is pretty awesome. I'm a geologist, so I get pretty psyched about this. But the Earth is great. It's powerful. It's dynamic. It's constantly changing. It's a pretty exciting place to live. But I want to share with you guys today my perspective as a geologist and how understanding Earth's past can help inform and guide decisions that we make today about how to sustainably live on Earth's surface. So there's a lot of exciting things that go on the surface of the Earth. If we zoom in here a little bit, I want to talk to you guys a little bit about one of the things that happens is material gets shuffled around Earth's surface all the time. And one of the big things that happens is material from high mountains gets eroded and transported and deposited in the sea. And this process is ongoing all the time, and it has huge effects on how the landscape works. So this example here in South India, we have some of the biggest mountains in the world. And you can see in this satellite photo, rivers transporting material from those mountains out to the sea. You can think of these rivers like bulldozers. They're basically taking these mountains and pushing them down towards the sea. Give you guys an example here, right? So we zoom in a little bit. I want to talk to you guys specifically about a river. You can see these beautiful patterns that the rivers make as they're pushing material down to the sea. But these patterns aren't static. These rivers are wiggling and jumping around quite a bit, and it can have big impacts on our lives. So an example of this is the Kosi River. So the Kosi River has this nice C-shaped pathway, and it exits the big mountains of Nepal, carrying with it a ton of material, a lot of sediment that's being eroded from the high mountains, and it spreads out across India and moves this material. So we're going to zoom in to this area, and I'm going to tell you a little bit about what happened with the Kosi. It's an example of how dynamic these systems can be. So this is a satellite image from August of 2008. And this satellite image is colored so that vegetation or plants show up as green and water shows up as blue. So here again, you can see that C-shaped pathway that this river takes as it exits Nepal. And now this is monsoon season. August is monsoon season in this region of the world. And anyone that lives near a river is no stranger to flooding and the hazards and inconveniences at minimum that are associated with that. But something interesting happened in 2008, and this river moved in a way that's very different. It flooded in a way that's very different than it normally does. So the Kosi River is flowing down here, but sometimes as these rivers are bulldozing sediment, they kind of get clogged, and these clogs can actually cause the rivers to shift their course dramatically. So this satellite image is from just 2 weeks later. Here's the previous pathway, that C-shaped pathway, and you notice it's not blue anymore. But now what we have is this blue pathway that cuts down the middle of the field of view here. What happened is the Kosi River jumped its banks. And for reference, the scale bar here is 40 miles. This river moved almost over 30 miles very abruptly. So this river got clogged and it jumped its banks. Here's an image from about a week later, and you can see these are the previous pathways. And you can see this process of river jumping continues as this river moves farther away from its major course. So you can imagine in landscapes like this, where rivers move around frequently, it's really important to understand when, where, and how they're going to jump. But these kinds of processes also happen a lot closer to home as well. So in the United States, we have the Mississippi River that drains most of the continental US. It pushes material from the Rocky Mountains and from the Great Plains. It drains it and moves it all the way across America and dumps it out in the Gulf of Mexico. So this is the course of the Mississippi that we're familiar with today, but it didn't always flow in this direction. If we use the geologic record, we can reconstruct where it went in the past. So for example, this red area here is where we know the Mississippi River flowed and deposited material about 4,600 years ago. Then about 3,500 years ago, it moved to follow the course outlined here in orange. And it kept moving and it keeps moving. So here's about 2,000 years ago, 1,000 years ago, 700 years ago. And it was only as recently as 500 years ago that it occupied the pathway that we're familiar with today. So these processes are really important, and especially here, this delta area where these river jumping events in the Mississippi are building land at the interface of the land and the sea. This is really valuable real estate, and there's some of the most deltas like this are some of the most densely populated areas on our planet. So understanding the dynamics of these landscapes, how they formed and how they will continue to change in the future is really important for the people that live there. So rivers also wiggle. These are sort of bigger jumps that we've been talking about. I want to show you guys some river wiggles here. So we're going to fly down to the Amazon River Basin. And here again, we have a big river system that is draining and moving and plowing material from the Andes Mountains, transporting it across South America and dumping it out to the Atlantic Ocean. So if we zoom in here, you guys can see these nice curvy river pathways, right? Again, they're really beautiful, but again, they're not static. These rivers wiggle around. We can use satellite imagery over the last 30 or so years to actually monitor how these change. So take a minute and just watch any bend or curve in this river, and you'll see it doesn't stay in the same place for very long. It changes and evolves and warps its pattern. If you look in this area in particular, I want you guys to notice there's a sort of a loop in the river that gets completely cut off. It's almost like a whip cracking and snaps off the pathway of the river at a certain spot. So just for reference again, so in this location, that river changed its course over 4 miles over the course of a season or two. So the landscapes that we live in on Earth, as this material is being eroded from the mountains and transported to the sea, are wiggling around all the time. They're changing all the time. And we need to be able to understand these processes so we can manage and live sustainably on these landscapes.
Okay, and I'll end there. You can pick up with the kind of the second half. Really cool to think about, river systems and how dynamic they are. I mean, just it's amazing stuff. I mean, I love rivers. I love lakes. I love, camping, of course. And I'm hoping that when you think about a river, next time you're standing next to one, think about some of these components of a river, these characteristics of a river that we're talking about in this lecture. Really kind of fascinating stuff if you think about all the various intricacies and aspects of rivers that maybe we take for granted. So anyway, all right, so that's rivers. We're going to talk a little bit more about Nisqually River in particular, and I might postpone that until Monday when I get back, just so that I don't overwhelm you with too many videos. So I think we'll postpone that one until Monday when I get back, and yeah. And so if you have any questions, go ahead and email them to me, and try to work on those worksheets, except for the part about Nisqually River in particular. We may go ahead and hold that one until the Tuesday when I get back. So we'll talk more on Monday of the following week. All right. Okay. Take care. Go ahead and send me emails if you have any specific questions. All right.